Hello everyone, I'm Ken Hanson. I'm an associate professor in the Department of Chemistry and Biochemistry at Florida State University, and here's my lecture on time-resolved emission spectroscopy. And so just a brief outline of what we'll be going through, just a general introduction into excited state dynamics of molecules and materials, and then we'll go into logistics of measurements by both frequency domain and time domain. We'll just briefly cover frequency domain, primarily focus on time domain measurements, and partition them by complexity of the measurement or the time scale of those various measurements, and then finally close with a brief mention about fitting those emission decays. And so when you talk about emission, steady state emission is the simplest measurement. It's very common to do. It's undergraduate general chemistry or analytical chemistry labs, where you essentially shine light on the sample and see what sample the color glows. And so putting this in a Jablonski diagram, we effectively excite the molecule or materials from the ground state to an excited state, S0 to S1. And then in that excited state, it can undergo either non-radiative decay or radiative decay, where it'll either be non-emissive or emissive. Non-emissive, it gives off heat. And so essentially, when you're doing a fluorescence measurement, that's exactly what you're measuring. You're measuring an equilibrium between the excitation process and the relaxation process. And so there's a constant bombardment of photons and a constant flux of photons coming off the sample. And so you get a graph that looks something like this. You have the wavelength or energy versus the intensity of the signal, and you get a curve that looks like that. And so again, it's an equilibrium. This gives you insights into the emission intensity, which if you know the photons going in, you can get the quantum yield of emission, and also the wavelength or the energy of that emission. Now, if instead of doing steady state excitation, you do pulsed excitation, you can get information about how long those excited state lifetimes live, not just an equilibrium condition, but a dynamic process that looks essentially something like this, where on the x-axis you have time, on the y-axis you have intensity, and so you have a pulse of light, and then once in the excited state, that material can relax down and give off light over time. And so you're effectively pumping to an excited state, and you have a competition between non-radiative and radiative decays. And so depending on the competition between them, that will dictate your lifetime of the material. And so that is essentially what your excited state lifetime is dictated by. And so when thinking about this on a single molecule basis, it's very different than thinking about an ensemble basis. And so we're going to take a molecule. I just use a simple example like anthracene, commercially available, bright emitter, nanosecond lifetime. And if you take a single molecule and you watch it change over time, which is essentially what we're going to do here, this is essentially an extended Jablonski diagram, where on the y-axis here we're going to say is time. And so we take an anthracene molecule and we excite it with a photon, and then after a given period of time, it can relax back down radiatively. It can give off a photon. We can excite it again, and then after a certain period of time, it'll give off a photon. And then we excite it one more time, and maybe it doesn't emit at all. Maybe it non-radiatively decays. And so when talking about single molecule behavior, it's a bit unusual and counterintuitive, but essentially after you've excited a molecule, it can stay in that excited state for any given period of time. Essentially, the lifetime for that single excited state can be from 0 to infinity. It's unlikely to be infinity, but it can be. And so essentially what we're doing is we're not measuring the lifetime of a single molecule of a single excitation event. Instead, we're measuring an ensemble of these measurements. And so essentially what we're going to do is take this measurement millions and millions of times, and what we end up with is a probability distribution, saying most of the time it's going to be this lifetime, sometimes it's longer, sometimes it's shorter, and that's effectively where this curve comes from. That every single photon that came off was a different single molecule emission event, and you compile those together to get this time-resolved emission versus time graph. And so again, you're measuring many single molecule emission events, and you're getting an ensemble behavior that looks something like this. And so what do I mean by that? Is when you have your sample, essentially you're going to shine light on it and you're going to excite some fraction of those molecules. And so in this case, we're going to excite half of them. This is completely unrealistic. You need a very, very powerful light source, but for the sake of this math we're going to do here, we'll say half these molecules get excited, and we have 64 excited states right after the pulse of light. And then we wait some time period X, and half those have gone away. And so we've effectively lost half our excited states. Wait another time period X, we'll lose another half of those, another time period, another time period, another time period. And as you can see, the number of excited states is decreasing over time. And so this is that image again. And so if we were able to count these excited states experimentally, we'd say it goes from 64 to 32 to 16 after time period, 1 time period, 2 time periods. And you get a graph that looks something like this, right? We started out at 64, now we're down to 32, so on and so forth. You're essentially getting an excited state decay. And so the thing about emission measurements is we don't count the number of excited states. Like you can do that via transient absorption, but emission, we're only counting the number of photons that come off the system. Well, it turns out the number of excited states is proportional to the number of photons related through the quantum yield. How good is it at emitting? And so effectively, when we do an emission measurement over time, we're counting those number of photons. And so let's say this has a 100% emission quantum yield, you get 32 photons from those 32 relaxed states. If this had a 50% quantum yield, you can cut that number in half, this number in half, so on and so forth. And so you end up with a curve that looks something like this, where at time x, 32 photons came off, time x2, 16 photons, 8 photons, so on and so forth. And so that's essentially what we're getting at with these time-resolved emission measurements. We want to count the number of excited states, or in this case, we want to get signal for the number of photons that come off the sample over a given period of time. And so for a molecule, or at least a well-behaved molecule, this is going to be an exponential decay. And that's just intrinsic to the decay processes associated with it. And so you can effectively fit most of these molecular species with this equation right here, where there's essentially an exponential relationship that's dependent on T, the lifetime of the sample. And so your intensity decreases over time, and you can fit that with an exponential and get an actual lifetime number here. And so this lifetime that we're measuring is equal to 1 over the radiative plus the non-radiative rates. Again, it's a competition between these processes. Does it give off a photon? Does it vibrationally relax? The combination of those rate constants, 1 over that gives you your lifetime of the system. And so based on this equation here, the tau that we get is essentially the time it takes for 63.2% of the excited states to decay. And so this is an intrinsic property to molecules. If you measure the same molecule in the same solution at the same temperature anywhere on the world, you should get the same lifetime because it's an intrinsic property of those molecules. And so we get decays that look something like this, essentially time versus intensity, and we get this exponential decay curve. Turns out if you graph this on a log axis, it's actually easier to see if it's a well-behaved exponential because you end up getting a straight line. So essentially here, instead of intensity, you take the log of intensity and you get a linear decay on a time versus log intensity graph. You can also do this for full spectra. Basically everything we've been showing so far is single wavelengths, just monitoring one particular energy over time. But you can do the same thing for full emission spectra. And so you can have graphs that look something like this, where at every single wavelength, the decay is similar, at least in this case, or you can get 3D representations of this, where you can actually see that exponential decay, but it's occurring across all wavelengths across this particular emission peak. And so again, if you have a well-behaved molecule, chances are you're going to get single exponential emission decays. And so why do we care about measuring this? A lot of different reasons. I mean, things like radiative and non-radiative rates are obviously correlated with lifetimes. You can also get all sorts of information like anisotropy, like rotational dynamics. You can get energy transfer, electron transfer, distance dependence of those events, depending on lifetime changes under certain conditions. And so obviously measuring this time-resolved emission ends up being a really important thing. And so back to our outline, there's two primary methods for measuring time-resolved emission, at least two general categories of it. So there's frequency domain and there's time domain. And so essentially frequency domain is a phase-modulated method, and a time domain is basically a pulsed method, so quick pulses of light. And so I'm just going to briefly mention frequency domain measurements because it's much less common than time domain, but it's still a really cool technique. And so what happens with a frequency domain measurement is essentially you're going to do a steady state emission measurement, but you're going to change the intensity of the excitation source. And so the idea is you do some kind of low intensity excitation in your sample and you monitor emission out of it. And then you change that intensity and monitor emission. And then you lower that intensity, monitor emission. And so essentially what you're seeing is an modulation in intensity. And so in this case, it's low intensity, you'll get low intensity emission, higher intensity emission, lower intensity emission. And so you effectively monitor this change over time. And so what you end up getting is a relationship between the excitation modulation, which is basically the intensity going up and down, and the emission modulation, which is again the intensity of the emission going up and down. And so from this relationship here, you can essentially back out changes in amplitude as well as changes in phase between the peak positions. And so this change in phase and amplitude is going to be dependent on the lifetime of the sample. And so, you can get a bunch of these parameters, and essentially you take oscillations in this frequency, and you can back out lifetime from these various different parameters. And so essentially this measurement, what you do is you have some kind of steady state life source, you have an excitation monochromator, and then you need something like a Pockels cell that can oscillate the intensity. And so you have some kind of controller that can oscillate the intensity of light that comes off the sample. It gets to the sample will emit, and the sample will respond to this oscillation and excitation source. And then eventually it's going to go to an emission monochromator, and you can have a detector where you essentially can detect changes in that amplitude over time. And then you have the master and slave communicating, and it basically says that, or tells you the time delay between the oscillation here and the oscillation here. And so from that, you can essentially get amplitude and phase changes. And so really cool technique. If you modulate the frequency, you can essentially back out what the lifetime of the sample is. And so the difference, the peak splitting, as well as the delay in the signal frequency tells you what the lifetime of the sample is. And so really cool technique. It's analogous to electrochemical impedance spectroscopy, where you oscillate a voltage and see what the lag in response is in terms of current. Very similar to that technique. And so I found papers where people did this in lifetimes as short as 10 picoseconds, which is pretty amazing. What's nice about it is you can measure with a continuous light source. You don't need to control the light source. You only need to control how you filter that and decrease and increase the amplitude and how fast you can do that oscillation. And it turns out because of that, you can tune it from the UV to the near IR. You just need essentially a filter that works with any of those wavelength ranges. One of the disadvantages is here's the list of commercially available frequency domain instruments. I could be wrong on this, but as far as I know, no one sells a commercially available instrument. There may be individuals that still do this measurement, but as far as I know, it's not a particularly popular way to do time-resolved emission measurements, because it turns out other techniques like TCSPC have become much easier and much more readily available, especially with the advent of ultrafast and even diode lasers and things like that. And so we skipped over frequency domain, or only briefly covered it again, because most measurements are done in the time domain, where you essentially have a pulsed light source. And so in time domain measurements, you're essentially looking at graphs that look something like this. And so essentially you have some kind of light source where you can do a very narrow, and by narrow I mean temporally narrow pulse of light. You flash that light on the sample get excited, and the sample will decay over time, as we talked about earlier, typically an exponential decay for a molecule in solution. And essentially what you want to do is monitor that emission decay over time. And so pulsed methods, these can get you down to as short as 50 femtoseconds. So I think the highest time resolution are time domain measurements. There's a bunch of different ways you have to do this measurement depending on what time scale you want to work at. Unfortunately, the source is typically not as tunable as the frequency domain, unless you have things like an OPA or an OPO where you can tune your laser pulses, which again are becoming increasingly popular and easy to use. So in terms of time domain, for photons coming off a sample, at least with molecular species, typically you're going to see fluorescence and phosphorescence, and then a bunch of events happening in between there. And so fluorescence can happen anywhere from femtoseconds to nanoseconds, and phosphorescence is typically nanoseconds up to seconds or even longer, depending on what the decay pathway is. And so you're covering 15 orders of magnitude time scale. And so the difficulty is you can't use one instrument to measure on the second time scale you can't use the same instrument to measure on the second time scale as you can on the femtosecond time scale. And so it turns out we need several different instruments and several different techniques to time resolve emission across these 15 orders of magnitude. And so on the longer time scale, we have these real-time measurements, watching the emission and detecting it in real time. Technique TCSPC, time correlated single photon counting, gets you a little bit faster, also gets you essentially can measure weaker and weaker samples. Streak camera is a modification of both of these techniques. It's basically a detection method that allows you to cheat beyond your standard detector. And then fluorescence upconversion is a technique. As far as I know, this is the fastest time resolution you can measure emission off of a sample. And it's somewhat limited as to how far you can measure. You can measure from femtoseconds to seconds or nanoseconds type time domain. And so what we'll just do is walk through those techniques, starting with the real-time lifetime measurement and then going to the faster and faster measurement time scales. And so a real-time measurement, the analogy I like to talk about in class is when we talk about glow-in-the-dark materials, essentially anything you have that glows in the dark at home, you put it in a bright room and then you turn off the light and you can watch it glow, and you'll see that glow decay over time. And so if you had a stopwatch and some way to, I don't know, quantify the emission that's coming off the sample, you'd say it's bright now, it's half as bright, it's half as bright, and you could actually time resolve the decay of that long-lived emission from a species. And so that's essentially what a real lifetime measurement is doing. And so essentially what you do is you have some kind of light source. In that case, it's room lighting, some kind of detector using something more standardized and accurate than the eye. And then you have a sample where you're exciting the sample, and then you can select your wavelength or do full wavelength detection. But the key to this is essentially knowing the time difference between your source and your detector. If you know when the pulse happened and you measure the light coming off after that, you can get time resolved emission. And so the measurement instruments look something like this. The basic procedure is you have some kind of light source that you can pulse. So this could be a laser, this could be a flash lamp. As long as you can shine light for a brief moment, you're temporarily exciting the sample. And so you have some kind of sample holder. Typically emission measurements, you're going to be perpendicular to prevent light from getting directly into your detector, or the excitation light getting into the detector. And then it's going to go through some kind of monochromator, or you're going to spread it out on a CCD detector or single wavelength detector, and you're going to be able to see at a given wavelength, how does the intensity off this sample change over time. And so that's essentially what you're doing, is you're going to plot signal, typically in voltage or current, and you're going to do that versus time from the pulse of a laser light. And so you get something that looks like this. And so this dotted line is essentially the laser pulse, or the width of the light source pulse. And then you're going to watch emission rise, and then that emission will decay over time. And so this pulse here is something we call an instrument response function. It basically says, here is the width of the laser pulse. This is the fastest you're going to be able to excite your sample. And the width of this, the width of your IRF, is going to depend on what source you have. Is it a flash lamp, which is essentially a xenon lamp with extra voltage applied? Is it a laser? Is it a pulsed LED, where you can get the full width half max of that IRF smaller and smaller and smaller? And so basically, in order to make this real-time measurement as fast as possible, you need to make your excitation pulse as short as possible, so your IRF to be as narrow as possible. You're also going to be limited by the time resolution of your detector, right? How fast can the detector see this light coming off the sample? And so again, this IRF and then your detector response dictate how fast you can measure the sample. And so typically for these real-time measurements, you're looking at lifetimes longer than 200 picoseconds. Getting shorter than that with this method gets harder and harder. And so what you essentially do is you repeat this measurement many times. And so essentially it's going to look the same every time, but you'll do some kind of excitation pulse. Then you're going to watch light come off the sample. And then you're going to do an excitation pulse, and then light comes off the sample. And so the distance between these pulses, or the time between them, that's essentially a repetition rate of your source, whether it's a pulsing laser or LED or flash lamp. And then you're going to measure the decay over time. And then essentially you're going to average this over and over again, and then get some kind of intensity versus time graph that looks like this. And so this isn't just an example where there are 100 or so averages. It depends on the intensity of your sample, as well as quantum yield and all sorts of properties of your sample. And so at FSU, we have a few different versions of these real lifetime measurements. So one of them is the Edinburgh LP980. This is hooked up with continuum laser and an OPO. And essentially what it has is this neodymium mag laser with a 5 nanosecond pulse width. It can shine light on the sample. And we're just going to measure emission in real time, either single wavelength with a PMT or the area detection with a CCD, where it gives you full spectrum data. And so with this instrument, we can essentially measure anything between about 5 nanoseconds and 10 milliseconds. Again, that 5 nanoseconds is essentially dictated by the pulse width of this particular laser, as well as the frequency of that laser pulse. The other one in my group, we have Edinburgh FLS 980. In this case, instead of a laser, it uses a xenon flash lamp, which is this guy right here. It's essentially a xenon bulb that you apply voltage to. It's basically a glorified photography lamp that does a very quick flash of light, and this gives us about 5 microsecond resolution. And so if we want to watch really long time scale stuff out to seconds or tens of seconds if we wanted to, we can do that on this instrument with that flash lamp there. All right, moving on beyond real-time lifetime measurements, we're going to talk about streak cameras briefly. Streak camera is essentially a detection method. It's not an independent measurement technique. It can be coupled to real-time or time-correlated single photon counting type measurements. So a streak camera isn't necessarily an independent technique, but it does give us a means of cheating in terms of detecting time-resolved emission. And so essentially what we're going to do is get a temporal profile from a spatial profile. And so the example I use in class when talking about this spatial to temporal transition is actually based on a laser pointer that I used to have. And so some laser pointers, in order to lessen the load on the material, have something called a duty cycle, which essentially it oscillates between on and off. And so what's interesting is under normal use conditions, you can't really notice this duty cycle because it happens very, very fast. But if you start swinging that laser pointer against the wall really quickly back and forth, you can start to see these on-off cycles. And so you'll basically see breaks between light on and light off on the wall. And so what's really cool about this is essentially if you know how fast your arm's going, you know your distance from the wall, and you know how long these light bursts are, you can essentially calculate what that duty cycle is. And so what you're essentially doing is taking spatial information as well as the velocity of your laser pointer moving back and forth to figure out the time that each one of these pulses took. So you're taking spatial information and translating it to a temporal profile. And so streak cameras essentially do the same thing, but instead of using an arm swinging back and forth, they essentially use a cathode ray tube type setup. And so anyone over the age of 30 probably remembers cathode ray tubes. They're the big TVs with the bulbous back end on them. The reason they have this particular shape is because they have a cathode ray that essentially generates a beam of electrons. Those beam of electrons are directed towards a fluorescent screen, and the location of that beam is dictated by these deflecting coils, or basically a bias that creates an electric field that moves electrons in the direction you want them to go. And so by controlling this in the XY direction, you can essentially direct the electron beam towards any portion of this fluorescent screen. And so wherever it hits, it's going to generate light. And so you have RGB pixels here, and essentially you streak this electron beam across the screen, and you can write an image by directing the beam where you want it to go. And so if you have a CRT, you can actually control this to some degree. If you just put a magnetic field, you can actually change the electron beam from the front of the screen. Kind of fun. Don't do it. You could permanently damage it, but nonetheless, it shows how you can control an electron beam with an electromagnetic field. And so a streak camera is essentially using this concept, this idea of taking spatial information and translating it to time, analogous to this laser pointer idea. And so instead of the laser pointer motion, we have a sweep rate that's dictated by the applied bias here. And so this sweep rate essentially dictates when the electron beam is going to hit up against the detector, and we can essentially take whatever this distance is as well as a sweep rate, and we can effectively back out the time it took to put the signal across this. And so ultimately you can get a graph that looks something like this. What's the intensity of it hitting here versus here versus here, and how much time did it take for the beam to spread out across the detector? And so again, you're essentially using the length and intensity to calculate a time-resolved emission decay. And so a street camera it basically is coupled to a real-time or TCSPC type measurement. You essentially have a light source that hits the sample. That sample gives off light that can go through a monochromator and eventually hit a photocathode material. And at that photocathode material, it creates an electron. And so that electron, or several electrons, will actually go through the street camera. You have a sweep voltage apply here, and that will sweep at a certain rate depending on what time resolution you want. And it'll essentially spread out that electron beam at this MCP. This will essentially generate photons, where those photons are generated and then eventually hit a CCD detector. And so again, the idea is you're using a sweep voltage here and you're spatially resolving things with the time being dependent on what that sweep voltage is. And so a street camera has several advantages. You can get direct two-dimensional resolution, and so you can get both temporal as well as wavelength. If you essentially spread out the wavelength across a CCD detector and then sweep it over time, you can get full spectra data over time. And it's also not detector limited, at least not the time response of the detector, because you're not asking the detector to respond quickly, you're just asking the detector to spatially resolve. And so your time is dictated by your sweep rates. Disadvantages: typically you need a high stability laser, limited time resolution. 2 to 10 picoseconds is still really fast. It's not quite as fast as fluorescent upconversion, but it's time limited relative to that. You do need frequent and careful calibrations of both the sweep voltage as well as your spreading out your signal on the detector, and these cameras tend to be expensive. I mean, they're more expensive than, say, a standard PMT detector, and so there's a cost-benefit analysis that has to be done when talking about purchasing or using a street camera. All right, so at FSU, we do have one of these street cameras, at least the Strauss Research Group does. They have a home-built system with this Hamamatsu street camera. It's essentially connected to a neodymium mag laser. And so I think they get something on the order of a 500 picosecond resolution type measurement with this setup. And so, yeah, you can use it to do time-resolved emission down to picosecond type timescales. All right, so the next technique we're going to talk about is time-correlated single photon counting. And so time-correlated single photon counting, also known as TCSPC, is analogous to the experiment we talked about earlier with a single anthracene molecule and exciting it and seeing how long it waits to emit, and then doing this over and over again over time to get a signal. And so again, the excited state of lifetime of an individual molecule is 0 to infinity, but when you sum all those together, you essentially get the probabilistic lifetime of that molecular species, and that's where your lifetime comes from. And so the way TCSPC works is it's a very low intensity technique where you essentially want a very small number of excited states. And so you do a low intensity pulse of laser light as narrow as you possibly can. And every once in a while, you're going to get an emission event. And so every 20 to 100 pulses, you're going to eventually detect an emitted photon. Ideally, it should be 0 photons, only 1 or 0 photons per pulse of light. And so it's analogous to single molecule imaging, except you're doing it on ensemble, but you're only exciting and detecting 1 photon at a time. And so the way this technique essentially works is you have some pulse of light that starts timing electronics, and those timing electronics will keep going until they get a signal from the detector, which basically says a photon has hit, and that is the time between the start and stop. And so the way this detection works is essentially it has detector bins where it says, did it come in this time window? Did it come in this time window, this time window, this time window? You have some time intervals after the laser pulse, and these are known as detector bins. And so what happens during this measurement is essentially you're going to do a histogram of signals falling within these detector bins. And so the idea is you're going to have 1 pulse of light, and then eventually a photon comes out in this bin, another pulse of light, no photons created, another pulse of light, and it ends up in this bin. And so essentially what your software is going to do is it's going to start summing this over time. It says between your start and stop time, we got a signal there, and then we got another one there, and we got another one there, and eventually it's going to build up a histogram. That essentially added histogram gives you something of a probability distribution. So it's measuring single molecule events, but it's adding them up over and over again, and it gets you a histogram that looks something like this. And so ultimately the data looks much more intensive, as in it has a lot more bins than what I represented there. And this is what a TCSPC signal looks like. So this orange is the instrument response function, and the blue is the actual signal from the sample. And each one of these dots that you see is essentially one of those bins. And so it's a histogram where this one has added up to here, this one to here, so on and so forth. Here's a general depiction of a TCSPC instrument. We don't have to go into all the details, but the general idea behind it is you have some kind of a light source, a laser or a diode or something that gives really short pulses of light. And essentially that goes to the sample here, S. And so that hits the sample, excites it, that sample is going to emit. And so that laser, if you have a beam splitter there, it's going to send a signal to start a basically a triggering event. So it gets some kind of signal to the tack, and so that's the time to amplitude converter that basically says now it's time to turn on. And at that tack, voltage is going to ramp, and it's going to keep ramping until it eventually gets a stop signal, and that's going to come from the emission off the sample. So you have a pulse of light, starts the tack, voltage going up, signal's going to come, or light's going to come off the sample. That's going to hit some kind of detector. That's going to give the stop signal to the tack. And what that's going to do is essentially translate that voltage into a temporal signal, because the voltage is going to be directly proportional to the time between the initiation and the stopping event. And so that essentially gives you your time for each single photon event. And so, like I said earlier, this is excite, detect one photon, excite, detect one photon, and essentially you're using the tack to figure out the time difference between the excitation and the detection pulse. And so that's how you start generating your histogram over time. And so each time that occurs, that gives you one single data point. Going back to this graph, essentially you're going to add up those single data points over and over again. Note this is a logarithmic scale. Your first point's going to go here, next one here, so on and so forth. And it's going to build up this TCSPC histogram. And so TCSPC, this is one of the more common time-resolved emission measurements at this point. It's a really sensitive technique. Like we said, it's single photon. Right, so essentially you can do very low, weak emitters, and you can still detect signal. It also gives you a relatively large dynamic range, 3 to 5 decades of time, well-defined statistics. This behavior has been well understood and well studied. There are papers that say you can get temporal resolutions down to 5 picoseconds, depending on your pulse width as well as your detector response time. It's very sensitive. Time resolution, like any measurement, limited by source as well as the timing electronics. And you can get these instruments for as low as 15K for a single wavelength light source. And so, yeah, a reasonable price for a TCSPC instrument. Disadvantages, this takes a long time to acquire data. Remember, you're doing it basically one photon at a time, so you need a whole lot of laser pulses to build up enough signal to actually get enough data to get a decay trace. There's complicated timing electronics, which mostly at this point are plug and play. Another issue is straight light, because you're relying on single photons. Any light hitting your detector is going to add to your noise, and so reduce your signal to noise. Other issues, you typically only want to do lifetimes that are less than 10 microseconds. So between that 5 picosecond and 10 microsecond window. And the reason is because of your essentially the nature of the measurement. And so if you have a molecule that has like a 10 millisecond lifetime, essentially you would need a repetition rate that's twice that lifetime, so a 20 millisecond repetition rate or 50 hertz. If you're going to measure a 1024 bin, which is a pretty standard, the number of essential boxes you're measuring for that 20 millisecond window, and you want to get 10,000 peak counts, essentially you're going to need over 4 million counts total. And so if it's 1 count per 20 reps, as in only get 1 photon per 20 repetitions, it's going to take you 20 days to measure a sample that has a 10 millisecond lifetime with these given parameters. And so essentially 10 microseconds is the longest you want to measure. Even that's going to take you probably a couple hours rather than 20 days. And so, yeah, lifetimes typically between picosecond and microsecond timescales. Anything longer than this, typically you're going to do the real-time laser flash or flash lamp type measurement. While TCSPC is a great technique and it's user-friendly and it's getting more and more common, there are a few common pitfalls that I just want to make everyone aware of. And so one of the issues is your repetition rate is too high. And so the general rule of thumb is you want a repetition rate that's twice the lifetime of your sample, but you don't necessarily know the lifetime of your sample ahead of time. And so generally I default to longer time scales, but there is an issue if your repetition rate is too high. And so what do I mean by that? Basically saying you have your molecule here, we'll say here's electrons in the ground state, we're going to generate an excited state with the laser pulse, and then let's say a real-time decay is between here and here, and then you get emission. The problem is if your repetition rate is too high and your next pulse of excited light comes in before decay from your sample, essentially what your system is going to think is that the start and stop time is this rather than this. And so what ends up happening is it's giving you an artificially short lifetime for that particular excited state. And it's going to do this over and over again because your second pulse is coming in before the molecular material has time to relax. And so the real start-stop time would be this. The artificial start and stop time will be here. And it's because your repetition is happening too quickly. And so what ends up happening is you're essentially overlapping your signal. And so your next excitation pulse is happening before your first emission decay could occur. And so what ends up happening is it's biasing the detection to shorter times than it actually is. And so essentially what ends up happening is the lifetime that you measure is going to be shorter than the real lifetime of the sample because it's artificially measuring the long tail and thinking that it's a shorter lifetime than it is. And so the general idea is keep your rep rate at least 10 times slower than your lifetime and default to longer times until you know what that lifetime is. So if you want publication quality data, figure out a rough estimate of your lifetime ahead of time and then set your rep rate to lower than that, at least twice, more likely 10 times slower than your lifetime. Another problem you could have is if your excitation source intensity is too high. And so this is going to do a slightly different version of what we talked about. Basically, if your light source is too intense, it means you're going to detect, or your sample is going to emit more than one photon per excitation pulse. And so this whole technique relies on single photon counting, where you excite once and one photon comes off. If more than one photon comes off, the problem is your detector only sees the first photon. And so your tach starts ramping up during the start, and then when that first photon comes, it shuts it off, and that's what the time it is. But if you're generating more than one photon per measurement, you're never going to measure that second photon. And so essentially all the really long stuff is not going to be detected at all when your intensity is too high. And so you end up with something called a pileup effect, where you're only counting the early photons, and so you're getting an artificially short lifetime. And so the same idea, your measured lifetime is going to be shorter than what the real lifetime actually is. And so the way you mitigate for this is keep your intensity as low as possible. Again, you're trying to limit the number of photons, or the number of detectable photons coming off the sample. And so typically what you do is have your stop count rate be less than 2% of the excitation rate. And so on the instrument, it's going to basically say, here's your excitation frequency, and here's how often we're detecting signal. And so if only 2%, that means 1 out of 50 of those excitations leads to a photon. Chances are you're not generating multiple photons per measurement. If you're higher than this number, there is a possibility you're going to have more than one photon, and you're going to get this pile-up effect, which gives you an artificially short lifetime. Another potential problem, and this only really becomes a problem if you're measuring really, really fast stuff and you're using a photomultiplier tube, but it's something worth noting nonetheless. So a photomultiplier tube, essentially, it doesn't actually multiply photons. Instead, it multiplies electrons. And so essentially what you have is a photon hitting the PMT photocathode. That's going to eject an electron. That electron is going to hit a dynode. That dynode is going to bounce back and forth, and each time it hits one of these, there's essentially a voltage drop across these that's going to create more and more electrons every time. And so the way a PMT works is it's taking one photon to an electron into many electrons, and then finally at your anode, you're getting much more signal than you would with just one photon. And that's why it's called a photomultiplier tube. And so really cool technology development in terms of detectors. This is why you can start detecting single photons, because you're not just getting one electron out of it, you're getting thousands of electrons out of it. But there is a potential problem with this, especially with time-resolved measurements, that you're relying on the photoelectric effect, which is essentially your photon's going to hit a material, that material is going to eject an electron. The speed of that ejected electron is dependent on the energy of the incident photon. And so let's say you need 2 eV to eject an electron, 700 nanometers, no signal, go down to 550 nanometers, that's 2.25 eV. That's enough intensity to eject an electron. But there's a little bit extra energy, this 0.25 eV, and that extra energy translates to additional velocity of this electron. And so the higher the energy, the higher the velocity of that electron coming off the detector. And so what ends up happening is if you're measuring higher energy photons, you actually get a higher velocity electron. It's actually going to hit this anode faster. And so you can actually have time differences depending on the wavelength of your sample. Again, this only becomes an issue when you're doing like low picosecond time scales, and so you really need to calibrate for differences in the electron velocity, especially if you're using, well, if you're using this photomultiplier tube technology. So again, higher energy photons give you faster signal. Your measured lifetime is going to be artificially lower than your real lifetime, depending on how you've calibrated this. All right, so in terms of TCSPC measurements at Florida State University, our FSU spectroscopy lab has the Horiba Fluoramax 4 in CSL 116. You can measure lifetimes. They advertise it as greater than 250 picoseconds. I'd be skeptical of anything under 500 picoseconds. In this case, it uses a nano LED light source. Here's a bunch of different wavelengths. And essentially there you can see your LDD, and then inside it has a PMT plus a monochromator to give you wavelength dependent. And so there you can see a TCSPC histogram essentially. Beyond that, there's several more in the department at FSU. Matusia has a fluorolog. My group has a TCSPC. Biwu Ma, Leonie House's group has a home-built system. So they're becoming increasingly common and really good for measuring lifetimes anywhere between roughly 1 nanosecond and 10 microseconds, like we said earlier. If you want to start measuring sub-picoseconds, like femtosecond timescale emission events, you have to start getting really creative with your setup, and that's where fluorescence upconversion comes in. And so basically the idea is, at some point, electronics like your source and detector can't communicate fast enough to do femtosecond type measurements. And so what fluorescence upconversion does is it essentially relies on, rather than source and a detector timing with each other, it essentially relies on a technique called sum frequency generation. And so sum frequency is basically this idea of taking two incidence wavelengths of light. We'll say here's a green one, here's a red one, and you combine them together and you get this purple guy. And so you're summing these two wavelengths together. You can do this with nonlinear optic materials, and you can generate a new wavelength that's the sum of the two individual wavelengths. And so for fluorescence upconversion, this gives you a really cool tool to start resolving timescales as low as 50 femtoseconds. And so the idea, again, is rather than relying on the timing between a source and a detector, instead you're going to rely on the timing between two pulses of light. And so I'll explain what that means in a second. So basically you have an incident beam of light here, and it's going through this BS, which is a beam splitter. And so you're essentially going to separate this light into, we'll say half goes this way and half goes this way. And so what happens with this particular beam of light is that's your excitation pulse. And so that's going to go through, you can tune the wavelength depending on putting it through an OPO and OPA, and eventually that's going to hit your sample, and your sample is going to give off light. And so the light that gives off the sample will get focused on in this case, it's a BBO crystal or nonlinear optic material. And so the other key part of this measurement is you're not just using one light source, but instead you use your beam splitter to have something called a gate pulse. And so this gate pulse basically goes through something that's called a delay line. And so it's basically a reflective mirror system that makes the wave or the light travel a further distance than the excitation pulse. And so it essentially goes through this delay line, gets bounced back and forth, and eventually gets directed at the same spot of the nonlinear optic crystal. And so what essentially happens is you have your excitation pulse hitting the sample gives off light, that light hits a BBO crystal, and at some point the gate pulse goes through and hits that same BBO crystal, and when those two incident lights come together, you can get a sum frequency. You can get additive effect of both of those light together and get a new wavelength of light that comes off the sample and eventually hits the detector. And so the thing about this measurement is it's only going to measure signal when you have summing both of those lights together. And so what it essentially allows you to do is to control when signal hits the detector based on when the gate pulse occurs. And so again, it's basically using the gate pulse to control when signal is actually seen, and that gate pulse is controlled by the delay line here and how far this light travels before reaching the actual sample. And so what do I mean by that? And so if you could measure infinite resolution real-time data, you'd have some kind of excitation pulse. you could see emission coming off the sample. But we can't detect these two independently, and so again, we have to get creative. And so the idea is you have those two different pulses of light. One is an excitation pulse, the other one is a gate pulse. And the time between these two is dictated by how much time the gate pulse spends in that delay stage. And so the longer that delay stage, the longer this time delay. The shorter the delay stage, the shorter this time delay. And so the key to this measurement is that you're only going to see emission off the sample when the gate pulse goes through. And so you're using some frequency, you're using the emission that comes off the sample plus this gate pulse, and you're going to sum those two together and get summed light at some time interval 1. And that's going to be dictated by this TD1. And so you change the path length of the gate pulse, you change the delay on the delay line, you make that distance it travels longer, and you can actually separate the excitation pulse and the gate pulse by a larger time interval. And so this is TD2, we'll say, and you're going to get some summed light at TD2. And you'll notice the amplitude of summed light is different because the intensity of the emission falls off over time, just as you'd expect. And so what you end up doing is, stepwise, you're essentially using, rather than being detector limited, you just keep your detector open, and you're using the gate pulse to control when the detector actually sees signal. And so if you know the path length that traveled, you know the delay time between the two, that summed light can be attributed to this time delay 1. And so you do this additively over time, change your delay stage, change the distance that gate pulse has to travel, and you're going to compile essentially an emission decay curve that looks something like this. And so again, the only time the detector sees the emission out of the sample is when the gate pulse and the emitted light come together, and the intensity of that signal is going to be dependent on the emission intensity from the sample. And so here you get an emission decay curve. And so again, it's a piecewise assembly of data. It's different than TCSPC in the fact that TCSPC, you have a detector and a source, they're separated. You're controlling the excitation pulse as well as setting the bins for detection. But in this case, some frequency generation, you're using the gate pulse to detect when light is actually coming off the sample, and it only measured the sum light. And so in this case, it's not detector limited like it is with TCSPC. For something like a PMT, you're limited by, say, a 10 picosecond response. In this case, you're limited by your delay stage as well as how well you can control the time distance between your excitation and your gate pulse out of the system. And so it's not limited by your detector. Your detector stays open the whole time, but the only time the detector sees light is when you have both of those incident lights, the emission plus the gate pulse, happening at the same time. And so going back to that original image, the key to this technique is effectively you're controlling time by the distance light has to travel here. And if you know that distance, you can actually calculate the time between the gate pulse and the time it actually hits the detector. And you can actually back out an emission decay curve that looks something like this. And so, yeah, again, it's a loophole where you don't have to rely on detector and source timing. Instead, you have to rely on two pulses of light where you control the time between the two pulses based on the distance that gate beam has to travel. And so the advantage, this is the very high resolution. This is, as far as I know, the fastest we can measure time resolved emission is using this fluorescence upconversion technique. You're mainly limited by your pulse width. Basically, how fast can you give those pulses of light? It might be sub femtosecond at this point. I don't even know if emission happens that fast on any given sample. Disadvantages, this demands a lot of alignment. This is a lot of optoelectronics you have to get working together. You have to align beams so they come in incident on the BBO crystal. It's a little bit limited in sensitivity. Basically, I mean, I think with our system, you need something like a 1% quantum yield to actually see emission. If it's weaker than that, it's going to be very hard to get signal out of it. And you have to have signal calibration. You have to know what your delay line, your distance and time relationships. And so it's a non-trivial measurement. But thankfully at FSU, we have one of these instruments. They're becoming increasingly user-friendly. There's commercially available instruments. In our FSU spectroscopy lab in CSL 3701, we have a coherent Estrella with an Opera Solo OPA that can tune the excitation wavelength. We have a delay line right here. And then right here is our ultrafast emission spectrometer, the Halcyon Fire from ultrafast systems. And so this allows us to measure emission decays between 250 femtoseconds and about 8 nanoseconds. And so you can see excitation and detection ranges. It really depends on what sample you're looking at, but again, ultra-fast emission decays, we can measure it on this system, and then there's our nanosecond TA setup. And so if anyone's interested, we have a user submission, or users can actually visit the facility to use this instrument. We spent all this time trying to get emission decay traces, so watching emission decay over time, at least with the time domain measurements. And the reason we're doing that is we want to back out a lifetime from them. And so that's where fitting the data comes in. So I'll just close with a brief mention of fitting these decay traces. And so a standard molecular emitter, under normal rules, will have an exponential decay curve. It'll basically have an exponential curve where the intensity changes with e to the negative t over tau. And so that tau dictates how sharp or drastic this curve is, and that tells you the lifetime out of the sample. But you don't always get exponential decays. In fact, it's not uncommon to get non-exponential decays, especially on unusual samples. And so single molecules, standard emitters in solution, you're going to get an exponential decay, but you can get things that look non-exponential in nature, or multi-exponential, or have some non-standard behavior. And so it turns out, if you do a log plot of the intensity, it's actually relatively easy to see non-exponential decays. So remember, I mentioned the time versus log of intensity graph. If it's an exponential decay, it's going to look like a straight line, and you can fit that with a straight line. If instead it doesn't look linear when you do this log intensity versus time, you have a non-exponential decay. And so the question is, what do you do with that? And so the reason you might have that is you might have multiple emitters. You might have an impurity that emits and has a different lifetime. Your sample could be inhomogeneous. This happens in protein structures where you have like a hydrophobic versus hydrophilic pocket. The emitter is going to behave differently in those pockets. You might have dual emission, a molecule that uniquely emits from two states. You could also have multiple emissive sites on a surface on peptides in a inhomogeneous polymer. Maybe one molecule is at a grain boundary and the other one's not, and you have emission lifetimes that are different. And so you might see multiple emission peaks, but you might also have multiple lifetimes associated with that. And so all these things can give you non-exponential decays. And so again, if it's a multi-exponential behavior or non-exponential behavior, on a linear scale, it might not be obvious to see. On a log scale, if it doesn't fit a straight line, then it's a non-exponential behavior. And so one option is to use something like a bi-exponential or tri-exponential fit. And so the idea basically being, okay, if we have some kind of non-exponential behavior, maybe it's the sum of two exponential decays. Let's say there's two molecules emitting and they have different lifetimes, and those lifetimes would be tau 1 and tau 2. And so basically what you're doing with this bi-exponential fit is you're saying, okay, on this log intensity versus time graph, you have two straight lines that are essentially summing together, one that has a 5 nanosecond lifetime, one that has a 50 nanosecond lifetime, and the amplitude at each of these contributions is dictated by this A1 and A2. And so you're literally summing together two single exponential decays, and it's giving you this bi-exponential behavior. And so if you have two emitters, you can potentially isolate their contributions with some kind of bi-exponential fit. And so, but there is a warning associated with this. You don't necessarily get a unique answer doing bi-exponential fits. And the reason is because you're limited by your signal to noise. And so, here's just a really fun example from Principles of Fluorescence Spectroscopy. Basically says, on a linear scale, this line right here, you can see both of these equations, these bi-exponentials, fit really well. And so you see different amplitudes of contribution and different lifetimes. And so one of them gives 5.5 nanoseconds and 8 nanoseconds. The other one gives 4.5 and 6.7 nanoseconds. And so on a linear scale, both of the fits look reasonably good. If you go to this log scale, so log of intensity or log of number of photons, you can see that the two fits diverge, but only a little bit down here. And so you can differentiate between the two. But the problem is a signal to noise issue. So basically at this 30 to 50 nanoseconds, you can see divergent between the two fits. The only problem is at this 50 nanosecond mark on a TCSPC measurement, for example, you're talking about a difference between 3 photons, right? And so if you're relying on a 1 or 2 photon signal difference, your noise is going to be so large in this region that you're not going to be able to distinguish between these two. And so you're going to get two potential answers depending on how the signal to noise falls and how the fits converge in this particular case. And so again, it's a complication with bi-exponential. You have a lot of parameters and you can get more than one answer. And so Just to show you an example of multi-exponential fits, here's just some raw data. This is actually from transient absorption, but the same idea applies. There's the raw data. You try to do a single exponential, that clearly does not work. Chi-squared is terrible. Residuals are all over the place. You can do a bi-exponential, a little bit better. It starts to, line up with the green, but you can see the residuals here. It's not really fitting that early time scale data. And so you can do a tri-exponential and you can get the curve to fit really, really well. But again, the more parameters you have, the more complex the model, the more you have to be skeptical of what you're actually getting. And so a really fun example of this, this is a story recounted in a paper. A turning point in Freeman Dyson's life occurred during a meeting of the spring of 1953, wherein Enrico Fermi criticized the complexity of Dyson's model by quoting Johnny von Neumann, "With 4 parameters, I can fit an element, and with 5, I can make him wiggle his trunk." And so it's basically saying, if you have enough parameters, you can fit anything, but doesn't mean it's actually physically meaningful. What's fun about this particular quote is it comes from a paper. Since then, it has become a well-known saying among physicists, but nobody has successfully implemented it. And so in 2010, these authors published a paper drawing an elephant with 4 complex parameters. And so they actually drew the elephant, then they had a mobile parameter to make it wag its trunk. And so again, the take-home message here is you can fit with more and more parameters and you'll get a better and better fit. But the question is it physically meaningful, and does it actually describe some physical phenomena, or are you just fitting for the sake of fitting? And so, yeah, you can find this on Wolfram Alpha and see the elephant wag its trunk, but kind of a fun reality check in terms of fitting your data. And so multi-exponentials are one option. Again, you could say there's contribution from individual species. Another option is a stretched exponential fit. And so this is a KWW fit. It basically assumes, rather than saying there are several individual single exponential behaviors, this one assumes there's a Levy distribution of rate constants. And so that's where this beta term comes in. Beta is a value between 0 and 1. It basically says there's a Levy distribution of exponentials, and those sum together to give you your decay curve. And so this beta parameter has at least some physical meaning. So when beta equals 1, it's single exponential. If it's less than 1, it means something else. There's also some power law modeling that you can do. And so in this case, you have this gamma parameter, and basically it assumes there's an exponential distribution rather than a Levy distribution. The point is these are describing different things. And so if you guys are interested in this fitting, I'd point you to this really fun paper. It's called Power Law Kinetics and Photoluminescence of Dye-Sensitized Nanoparticle Films. This was out of Chris Fecco and Ian McNeil when they were at UNC Chapel Hill. But it has this really nice graph basically saying, these fits mean something, right? A single exponential assumes one barrier, and that barrier is associated with a rate constant. Bi-exponential assumes 2 different things going over 2 different hills. And then you can go to things like power law, which is an exponential distribution of barriers, or a KWW that has a Levy distribution, or an Alberry model where there's Gaussian distribution. Every time you're fitting the data, you're basically making, at least you're implying that there is some physical phenomena behind the fit that you're applying to the system. And so if you do a tri-exponential, you're saying there are 3 independent processes that have exponential behavior, and here's what their lifetime is, and here's what their contributions are. And so take a look at that paper and read a little bit more in depth on these fitting methods. This is for dye electron transferring into TiO2, but the same general principle applies anytime you're fitting whatever your material is. And worst case scenario, you can resolve to a half-life of your sample, which is basically the time it takes half your signal to decay. So if none of the fits work, or you don't want to apply a physical model to the systems, the lowest hanging fruit is to simply say the half-life. And so here's our time versus intensity graph again. The half-life is simply, here's max intensity. What is half that intensity? Go over to here. There's the intensity 1/2. That's your lifetime right there. And so it's not uncommon to use a T1/2 to compare within a system. The qualifier you have to give is, you can have very different curves that give you the same T1/2. And so both of these start at the same initial intensity. There's the T1/2. Clearly the blue line is doing something very different than the red line. And so the red line might be an exponential decay. This might be bi-exponential. The point is, if you use T1/2, you get the same number. And so I would caution against using T1/2 unless every single one of your curves looks very, very similar. So you can say whatever T1/2 we're seeing, it's the result of a similar phenomena that's happening across the board. But as soon as these shapes change, T1/2 isn't going to work, and you'll have to figure out a more complex model like multi-exponentials or KWW models. It really depends on the behavior of system and what comes out of it. All right, so that's the end of my talk on time-resolved emission. Just a few shout-outs. I stole a bunch of the images and figures from Principles of Fluorescence Spectroscopy. Lakowitz goes into detail on time-resolved emission as well as measuring energy transfer. Mikas Venguris from Vilnius University, he has a really cool teaching materials page where he has, I stole the fluorescent upconversion images from him. He also has a bunch of text describing this stuff in much greater detail than I have. So if you guys are interested, check these out and getting more information about time-resolved emission and much more of the detailed aspects of that. But that's all I have for now. Thank you for listening. Good luck with your time-resolved emission measurements.